Hey everybody, and today's lesson we are actually going to be covering two topics. The first topic is independence versus dependence, and the second topic is going to be about two-way tables. Alright, so let's go ahead and get started on independence and dependence. So before we get started, you need to be aware of the definition of independence. If two events are occurring, the probability of one event occurring does not affect the probability of the second event occurring. So we actually can figure it out mathematically. We know that if A and B are independent, then the probability of A intersection B must be equal to the probability of A times the probability of B. Please keep in mind that this is very different than mutually exclusive. Okay? So just keep that in mind that independent and mutually exclusive are not the same item. And what you see here is actually called the multiplication rule for independent events. So up here we have some examples of independent events. Let's say we flip one coin and then we flip another coin. The odds of me landing on heads or tails does not change based on if the first coin was heads or tails. If I have two dice and I roll the first one and get a 1, the second die will still have a 1 in 6 chance of rolling a 1, regardless of what I rolled on the first die. Alright, choosing two cards with replacement. And with replacement has been bolded because that's the key part here. If I have a deck of cards and I draw a card, with replacement means I put it back in and then draw another card. If I don't replace it, that affects the probability. So you have to make sure that if it's independent, you replace the card before you draw a second. Alright, are these events independent of each other? Okay, if you take a look here, person A is left-handed. Let's say that the probability of being left-handed is about 20%. Sorry guys, that was my phone. My text tone right now is from Big Hero 6 when Baymax does the ba-la-la-la. So maybe I'll ask you what movie my new text tone is about. So we'll include that. Okay, so let's say the probability of being a person that is left-handed, let's say about, 30%, so 0.3. The probability that a person's the only child, let's say, is, 20%. And then a person being blue-eyed is 40%, okay? If I am an only child, does that affect my probability of having blue eyes? And the answer to that is no. Okay, I would still be 40% likely to be a blue-eyed child, irregardless of if I am an only child or not. So since these probabilities are not affected by each other, meaning that if I am an only child does not affect my percentage of being blue-eyed, then the answer is yes, that these are independent events. Now recall earlier I said that independent events and mutually exclusive was not the same thing, and here's a prime example of that. While these events are independent, meaning that their probabilities do not affect each other, they are still overlapping. A person can be both left-handed and an only child, or be left-handed and blue-eyed, or all three. So these are not mutually exclusive events, however, they are independent events. So what about these two events? Are these events independent of each other? Waking up late and getting to school late. Does the probability of getting to school late change if you wake up late? And the answer to that is yes. You could be late to school because of any number of reasons. Traffic, he had a minor emergency that morning, it's raining, whatever. But if you wake up late, you're going to increase your chances of getting to school late. So because the probability of B is affected by the probability of A, these are not independent events. Alright, so let's keep on with the theme of getting to school. Let's talk about a traffic light. Suppose that there are 6 traffic lights as you are coming to school. Each traffic light is independent of each other, meaning that just because you stopped at a red light on one light does not affect the chances of you getting stopped at the red light again for a second light. The lights have a certain probability of you being stopped at them or having green light. Okay, just because you were stopped at a previous one does not mean that you're not going to be stopped at the next one. Okay, so let's just say the probability of being stopped at any red light is about 0.6. So what is the probability of not being stopped by the red light? And that's where our complement rule comes into place. It's simply 1 minus 0.6 or 0.4, because either you will be stopped at the light or you won't be stopped at the light. Either you will go through it or you won't. Okay? So now, what is the probability of not being stopped at any of the 6 lights that you take to get to school? Well, each probability, okay, for each light is 0.4, and there are 6 of them. So what you're going to do is it's actually going to be 0.4 times 0.4 times 0.4 times 0.4 times 0.4 times 0.4, or 0.4 to the 6th power. So that's 0.004096. This is the probability of not being stopped at any red light, any of the 6 red lights on your way to school. If you want to think about this in terms of percentages, that's 0.4%. 0.4%. And the probability is 0.004. This comes from the multiplication rule for independent events. So in case you're wondering, this is the multiplication rule for independent events that I just talked about. So what is the probability of being stopped at least one light? Basically, in our previous problem, we had said, what if we don't get stopped at any lights? We found this probability. The complement of that is being stopped at one or more lights, so at least one light. So you would do 1 minus that 0.4, that 0.004096 to get your probability. Excuse me, wrong way. There we go. So 0.9959. So you have a 99.59% chance of being stopped at least one red light on your way to school. And that makes sense. All right, so let's look at this example. The odds of hitting a bullseye are 1 in 20. What is the probability that you will throw 2 darts and they both hit the bullseye? When I throw one dart, I have a 1 in 20 chance of hitting the bullseye. When I throw a second dart, the dart doesn't know, hey, she already hit a bullseye, so let's make it a little harder. No, you still have a 1 in 20 chance. So by the multiplication rule for independent events, this is 1 over 20 times 1 over 20, or 1 over 400, or as a decimal for probability, 0.0025. And that would actually be independent. All right, that's all for independence. Let's go ahead and talk about our second topic for today, two-way tables. So if you take a look here, we're going to do some review on our previous video. Here's a picture of a Venn diagram talking about 2 different things. Students who are in a foreign language class and students who play a sport. Remember that this number out here, this 3, means that I can either play a sport or in foreign language. All right, so we have a total of 50 students. How many students are taking foreign language? If I asked all 50 of these kids to raise their hand if they're taking foreign language, I would have these 23 plus these 14, which gives me 37. How many students play a sport? I have these 10 and these 14, so I make 24. How many students do both? That would be this green area of 14. How many students do not play a sport and do not take a foreign language? That's going to be these 3 kids out here that do neither. How many students play a sport but do not take a foreign language? That would be these 10 in the blue section, because these 14 right here are green, and they will take a foreign language as well. So that's not what we want. So let's make that a 10, not a 16. There we go. All right, now that we have that refresher, let's talk about two-way tables. Here's an example of a two-way table. Okay, it is actually based on this Venn diagram that we did here. You'll notice I have 14 people who play a sport that also take a foreign language. I have 10 people who play a sport but do not take a foreign language. That gives me my 24 total students. Of those who don't play a sport, 23 take a foreign language and 3 do not take a foreign language. That's 26. So you'll notice that I have several rows here. These are my totals here and here. And when I add the row, this total row here, and this column row here, I should equal my total 50, which I do. So what we have here is a two-way table that describes the Venn diagram that we just looked at here. Alright, so let's take an example here. It's 80 students were randomly polled, and they want to know if they prefer math or English. Now here's what I would do. Before I get too far, I would create my total rows. I'm going to do that right now. Alright, so I've created my total rows and total columns. The total number of 9th graders is 10 plus 12, or 22. The total number of 10th graders is 12 plus 11, or 23. 11 plus 8 gives me 19 11th graders, and then I have 16 12th graders. All I did was add each column. Now let's add how many people like math. 10 plus 12 plus 11 plus 8 is 41. And adding up English is 39. So if I add up 41 and 39, I get 80. If I add up 22, 23, 19, and 16, I get 80 as well. I know I filled in the totals correctly because the original problem said 80. So now that we're done setting up our totals, let's go ahead and figure out the probability of a student who would randomly like math, a randomly selected student who likes math. So out of all of the 80 students, 41 of them like math. So we're going to do, should be 41 over 80, which is 0.5125. So what's the probability of picking a junior who likes English? So out of the 80 kids, a junior who likes English, there's only 8 of those guys. So 8 out of 80, or 0.1. Alright, so here's my next two-way table. I'm going to go ahead and do my totals. 78 people vote yes for the library, 72 vote no. For the arena, 51 voted yes, and 99 people voted no. So when I add these, I get 100, and that is correct, or excuse me, 150. Okay. And that is correct because I have 150 voters. So if you are given that a voter plans to vote no to the new library, so I'm looking at these groups of people here, out of 72 people, what is the probability the voter also plans to say no to the arena? So that would be these people right here that vote no to both the arena and to the library. So 42 out of 72 is 0.58%, or 0.58 or 58%. Alright, so let's work on constructing a two-way table given some information in the paragraph. Alright, Felipe has surveyed students at his school and he found that 78 own a cell phone and 57 own an MP3 player. So that's where these two numbers come from. Alright, he said there are 13 students that do not own a cell phone but own an MP3 player. So no cell phone but own an MP3 player. So 13 is going to go in this spot here. Okay? Then 9 students don't own either one. So no cell phone, no MP3 player, that would be 9 students. Okay? Construct a two-way table summarizing the data. Now here's what we can do. I know that 57 students in total own an MP3 player. 13 don't have a cell phone. So 53 minus 13 means that there are 44 kids with both a cell phone and an MP3 player. Now looking at this column, 78 kids own a cell phone. If 44 have an MP3 player, then I subtract and I get 34 own a cell phone but no MP3 player. So now 34 plus 9 means there are 43 kids who don't own an MP3 player. 13 plus 9 is 22 kids who don't own a cell phone. So if we were to add the total column and the total row, we would get 100 total students surveyed. So if you're given that a student does not have a cell phone, so there's 22 kids who don't have a cell phone, what is the probability that they will have an MP3 player? So 13 out of 22 is going to give me 0.59 probability, or 59%. Alright, this video will actually continue on into a part 2. I'll see you guys there. Alright, welcome to part 2 of independent, dependent, and two-way frequency video. What we have here is we have non-disjointed events or not mutually exclusive events in a two-way table. Remember that this is the formula. You would add the probability of A plus the probability of B, and you would subtract their intersection. Okay? So what we actually have here is what is the probability of choosing a male or someone employed. So if we look, there are 499 males out of 1,000. That is the probability of A. Whoops. Alright, and then we want to add the probability of someone who's employed. So if we take a look here, I have 926 employed surveyors out of 1,000. Now if you notice, what happened here is we actually added this guy, and this lady, and we added this guy twice because he falls under the male column and the employed column. So what we need to do is we need to subtract the 459 guys, the employed guys, that we accidentally added in twice. That's why we have that subtraction up here, the probability of A intersection B. So when we do this math, the probability would be 0.966 or 96.6%. Quite a bit. Alright, so let's look at our last example. Deborah and Matthew are awaiting a decision about a promotion. Deborah guesses that her probability of getting a promotion to be 0.7, while Matthew's probability to be 0.5. Deborah thinks the probability of them both getting promoted is 0.35. So before we begin, we must figure out, are these two events independent? Is the probability of Deborah getting promoted times the probability of Matthew getting promoted, is that the same as the probability of Deborah and Matthew getting promoted? So probability of Deborah is 0.7. The probability of Matthew is 0.5. Is that equal to 0.35, which Deborah says is the probability of them both getting promoted? So let me fix that. And the answer to this is yes. So that means that these events are independent. Alright, so let's take a look at this two-way table. This is Deborah and this is Matthew. Deborah's, the probability that both Deborah and Matthew would be promoted is 0.35, so it goes here. Okay. We also know that just Matthew being promoted is 0.5. And Deborah being promoted is 0.7. So what we can actually do is we can take this 0.7 and subtract the 0.5 to find out that there is a likelihood that Deborah will be promoted but Matthew will not, is to be 0.35. The probability that Matthew is promoted but Deborah is not is going to be 0.5 minus 0.35 or 0.15. Then this right here, you're trying to figure out, okay, well, what do I add or subtract for this? What I notice here is that my sample space, the probabilities, must add to 1. So 1 minus 0.7 is 0.3, and 1 minus 0.5 is 0.5. So now following this information, I can say that 0.3 minus 0.15 is 0.15. You could have also said 0.5 minus 0.35 is 0.15. So this would fill in the two-way table. So the probability that neither one of them would get promoted is 0.15. So we don't actually have to fill in numbers like what we did with the cell phone and the MP3 player. We can actually fill in the probabilities. And when we fill in the probabilities, your total will add to 1 because, remember, the sample space of any events or any series is going to be 1. Alright, that's it for part 2 of independent, dependent, and two-way tables. I'll see you guys later.